Hello, I'm going to be doing the next 5 questions, part of this 10-question SAT Math Hard Practice quiz set. I'm going to try to be doing this on my computer. Hopefully this is probably better and it's probably going to be a lot cleaner. So let's do question number 6. A particular integer n is divisible by two different prime numbers p and q. Which of the following must be true? When they give me these questions, like which of the following must be true between 1, 2, and 3, what I like to do is I like to go through all 3 choices and I try to prove them false. So let's go with number 1. N is not a prime number. So looking at this, I could already see that I cannot prove this false. And once I know that I cannot prove it false, it might help to try to prove it true as well. But if you feel like you can't be proven false, then just go with your gut and just be confident that it will be proven true. But this one I can actually prove true. So let's go. So n is not a prime number. So the n is divisible by two different prime numbers p and q. So if a number is divisible by both two different numbers, we know it's not going to be a prime number because a prime number is only divisible by by one n itself. So let's say we have two different prime numbers. We're going to have 2 and 3. We know, and then multiply together is going to be 6. So we know that 6 is not going to be a prime number because it has these two factors, 2 and 3. So we can already say that 1 is proven true. Let's look at number 2. N is divisible by PQ. So you could already see if a particular n divisible by two different prime numbers p and q, we know that p and q both must be factors of this integer n. So that means in order to get this integer n to be divisible, they have to be factors, right? So that means they're going to be q times q times whatever other numbers, and they're going to be whatever numbers, and then as a result n is going to be divisible by p and q. So we know that then n is going to be divisible by p and q. So number 2 is going to be likewise true. Number 3, n is an odd integer. So let's try to use my tip and let's try to prove it false. So one way that we could just easily see this is that 2, anything you multiply by 2 is going to be an even number. So n can be divisible by, let's say, 2 and 3. 2 times 3 is 6. 6 is not an odd integer, it is an even integer. So 3 is proven false. So 1 and 2 are correct. So that means the correct answer is C. So for question 6, the correct answer is C. Let's do question 7. A perfect square is an integer that is the square of an integer. Suppose that m and n are positive integers. Wait, I just want to check that I'm recording still. Okay, I'm still recording. A perfect square is an integer that is the square of an integer. Yes, yes. Suppose that m and n are positive integers such that m and n is greater than 15. If 15 m n is a perfect square, what is the least possible value of m and n? This is kind of tricky, actually. So suppose that m and n are positive integers such that m and n. So there's two different ways you could approach this problem. One way is if you could just do guess and check. So basically m and n greater than 15. So that means m and n can't be greater than 15. So that means it has to be greater than 15 times 15. Where m and n is equal to 15, let's just say, and then there's 15 from here. So it has to be greater than this value. So that means anything greater than 15 squared. So now basically what you would do is you would guess and check. You would do 16 squared. Is it divisible by 15 squared? Is it divisible by 15? Probably not. And you go through this logic. So anything that is whenever you multiply by something by like 15, or like if you multiply by something by 5, you're going to have to get you're either going to get, your ones digit is either going to end in 5 or 0. For example, 15 times 1 is equal to 15. 50 times 2, 30. And you'll continue the pattern. So that means if you want to get something that will probably be divisible by 15 times a m and n, which will be a square, so we could do 15 squared. We can't do that. 16 squared, the ones digit is going to get end in 4. And you can see that by 16 times 16. What's 6 times? Oh, sorry. It's going to end in 6. The ones digit is going to end in 6. 36. And then when you saw that the ones digit is only affected by this part of the multiplication, 6 times 6, 6 times 3, 9, blah, blah, blah. So then we could see that the only numbers that will have a ones digit of 5 or 0 are going to be 20 squared, 25 squared, and 30 squared. And then you would check which is divisible by 15. 20 squared and is not divisible by 15. 25 squared is not divisible by 15. 30 squared happens to be divisible by 15. 30 squared is equal to 900. And 900 divided by 15. Do this on my calculator. 900 divided by 15 is equal to 60. So what is the least possible value of m and n? It's going to be 60. Well, m times n is going to be 60. A better way to actually probably do this problem instead of like guessing checking is try to reason it out. Let's see, suppose that m and n are positive integers and m and n are greater than 15. So one way you could do this is that you know that this has to be a perfect square. What you could do is then separate 15 into its factors. And an interesting way to look at squares is, let's look at 9. It's going to have 3 times 3. Obviously, 4 is 2 times 2. 25 is 5 times 5. What you can see is that you're going to have mirrors of different factors with the same factor. So, obviously from here, how can we mirror 5? You can multiply by another 5. How can we mirror 3? We could obviously multiply by 3. But this just gives us 15 times 15. And we know that m and n, we're just going to say this part is m and n. It can't be 15. It has to be greater than 15. So what is the least mirror, which is the least pair of mirrors that we can multiply to this m and n to still get a perfect square while minimalizing it, because we need the least possible value. So we could try using the pair 1 and 1. So times 1 times 1. But we know that's just 1 times 1, so we can't do that. Let's just do times 2 times 2. That's our second smallest. That's going to be 15 times 4. That's going to be 60. And we got the answer from the guess and checking, so to say. And the way this works again is that this whole value is m and n. This is 5 times 3 equals 15. We're trying to match 5 and 3 because we're trying to get a square. Because we could then divide this into two different sets which are being multiplied together. There's going to be 5 and 5 and 5. So let's put a 5 here, a 5 here. We have 3 and 3 times 3 times 3. And we got 2 and 2 times 2 times 2. So that is going to be 30, 30, 30, and 30 squared is 900, and then 900 divided by 15 is 60. So that's interesting when we solve that problem. So let's just write 60. All right, 8. M is a set of 6 consecutive even integers. When the least 3 integers of set M are summed, the result is X. When the greatest 3 integers of set M are summed, the result is Y, which of the following is true. So when you deal with problems that give you 6 consecutive even integers, what you would do is you would name a variable for the least number in that set, like least numeral value of that set. So let's call it n. And let n equal to least number in set. So now we get the information is a set of 6 consecutive even integers. So consecutive even integers, 2, 4, 6, 8, all consecutive, all even. We know they have a difference of plus 2, plus 2, plus 2. So that means in the set, what we're going to be dealing with is n, which will be our first least number in our set, then n plus 2, n plus 4, n plus 6. And we need 6. N plus 8. What else is there? N plus 10 is a 6. 1, 2, 3, 4, 5, 6. So we have these 6 numbers. 1, 2, 3, 4, 5, 6. Now all I have to do is plug stuff in. Let's see. The least integers result is x. So basically n plus 2 plus 4 is equal to x, while the greatest of the 3 integers of the set, which are going to be n plus 6 plus 8 plus n plus 10 is equal to y. So then I guess solve 3n plus 6 is equal to x. Here this can be 3 and plus 10 plus 8 plus 6. I don't know what that is. It's probably 24. Yes, it is 24. Wow. Look at me. So 3n plus 24 is equal to y. So now we need this in the form of one of these, where we only have y and x and we don't have n together. So just looking at this, I guess you could solve it through like a system of equations, I guess. Not really. Sorry, not system of equations. We don't have 2 different variables. We know that the way I'll approach this is that I see that there's a 3n here and a 3n here. We want to get the 3n to go away. So what happens if we substitute one of the 3n's in the equation so we could get 3n away? So we could just look at it here. 3n is equal to... Here, let me actually... Ooh, that's cool. 3n is equal to x minus 6. You know, 3n is equal to x minus 6 from this part, and we could just plug x minus 6 into 3n, which we have here. 6 is 24 is equal to y. See, y is equal to x plus 18. And our answer choice is B. Yay. Time to go erase. Bye-bye. Bye-bye-bye. Bye-bye. 2 more questions left. Let's go. 9. So number 9. A 3-digit number xyz is formed of 3 different non-zero digits x, y, and z. A new number is formed by rearranging the same 3 digits. What is the greatest possible difference between the 2 numbers? Okay. So the way I approach these problems is, let's see, they're going to be asking what is the greatest possible difference between the 2 numbers. So what I'm thinking is we get x, y, z, we find the greatest possible value, and then the least possible value for x, y, z, and then we subtract those 2 together. Well, rearranging them. So now we got that. How are we going to approach this? Immediately what comes to my head is when I make x, y, z to be its greatest, I'm thinking, oh, in the hundreds place, because that's where you're going to get your most value for the number, you're going to want to put your highest number. And what's the highest number from our decimal system? 9. We're going to want probably the first digit to be 9. Now we want to get the same, so let's just say x equals to 9. So now we have a different combination, right? So when we make the smallest number, we don't want to put the 9 in the hundreds digit, because we don't want to put the 9 in the hundreds digit again, because yikes, that's gonna be another huge number. We do not want that. And the tens digit, yes, you're gonna get a value of, let's say 9 times 10, 90. You're gonna get a value of 90 that is gonna be a part of this number. But why can't we go for, that's still too big for this small, we want the smallest number. So we should put the 9 in the ones digit. Put the 9s in the one digit because that it won't affect as much. Because let's say you have, which is bigger? Let's say 109. 190. Obviously this is kind of rough, but when you put your 9 in the ones digit, you're gonna get the least, you're gonna get the smallest number because you're giving it the least decimal value. So now we know that the 9 has to be here and the 9 has to be there. How can we make this number very small? Because we're trying to make this XYZ combination very small. Well, my head, I'm thinking we should definitely make the hundreds digit 1. This will give us our greatest net value. But we also need a 1 back into here in this part of XYZ. So where should we put 1? So we'll get the least. We'll get the, we won't impact it. We want the greatest number, of course. So we want to affect, because 1 is obviously a small number. We want this to affect it the least. If we put in the tens digit, we're going to get 9, 1, and something. But I think the best idea is to put into the ones digit, because now we have space to make whatever y to be as big as possible. So we're going to put our ones here at z, because we can make y as greater as possible. So we have 9, 1, 1, 9. Now, however, we see that no matter what number we put in here, let's say we put 8, this number has to be 8. And so on and so on. This number has to be 7. Then we're going to have to make this number 7. So you know that this is always going to cancel out, right? So you could put whatever number you want to here. I'll show you. You put 8, because you're putting the same numerical value for the tens digit. So you have 981 minus 189. What's that going to be? Take my calculator out because I can't do simple subtraction. 792. Let's say you had 971 minus 179. It's going to be, from my calculator, 792. It's the same, no matter what. But we have our greatest here, and we have our least here, and that's all that matters. And then we obviously try to offset it by putting the 9s here and the 1 here to get the greatest possible for this one and the least possible for this one. So, yeah, pretty interesting. So 792 is going to be our answer. And it's nice and all. Let's go to 10. An integer is subtracted from its square. The result could be which of the following. So again, we're going to go through all the answer choices, try to prove each one false until we can't prove one false. Get that out of the way. Integer is subtracted from the square. So when you deal with these type of questions, it's sometimes easier when you get an algebraic expression for it. An integer is subtracted from its square. Let x be the integer. Let x be integer. So an integer is subtracted from its square. So if we write this out in terms of an expression, it's going to be x squared. An integer is subtracted from a square, and then you're squaring it, and then you're subtracting it by that integer. So I guess we could even make this look even prettier. Let's distribute the x out. Nice. That looks nice and pretty, because x times x is x squared, x times 1 is x. So the result could be which of the following. Let's check A, a negative integer. Can this value become a negative integer? So let's test this. Seeing this, here you could guess and check, try to do your best, but you can also reason this out. Let's say we could use, let's check 1. If you put a 1 in here, 1 minus 1, 0, times 1 is going to be 0. 0 is not a negative integer. Let's try to put a negative integer. Let's put negative 1. Negative 1 is negative 1 times negative 1 minus 1. That gives us negative 1 times negative 2, just 2. That gives us positive integer. Let's even put 0. 0 here. Anything multiplied by 0 is just 0. So I'm not getting this negative integer. I just put a neutral value. I put a negative value, and I put a positive value. And we could see from here, x squared minus x, that no matter a squared value, if it's an integer, it's always going to be greater than just by itself. If we don't look at 0, 1, and negative 1. Let's say we put 2. 2 squared is 4. 4 minus 2. 4 is always going to be greater than 2. You will never ever get negative. 3 squared, 9, is always going to be greater than 3. You won't get a negative integer. Let's try putting negative 2. Negative 2 squared is going to be 4. But what you're going to do is you're going to be subtracting a negative number. It's going to be negative times a negative number. So that's going to be plus. So you're just adding. And anything squared with a negative is just going to become positive. So you know that a is not it. We do not like a. No me gusta a. We're not going to like a. And, oh, I didn't want to do that. I'm sorry. Let's just, oh, I don't want to, oh, I messed this up for myself. Wasn't that nice? Okay. I'm going to keep this part, because this is pretty pretty. This is pretty pretty, yeah. This is pretty nice. An odd integer. So, an odd integer. So can we ever get this to an odd integer? That's might be what you're thinking. Again, we're going to check this. Oh, this is pretty funny. The way you do this is like you're going to reason out as you keep plugging in numbers. Let's say you put 1. 1 times 1 minus 1 is 0. You're going to get 0. That doesn't work. Negative 1? Negative 1 times x minus negative 1 minus negative 1. This is going to be 2. So you're seeing that you're not getting these odd integers. Why? Well, you're going to realize that whenever number you put in here, let's say you put x is going to be an even number. Let's say you choose any even number 2. Well, any even number multiplied by whatever it is always going to be even. Right? Let's say 2 is an even number. Multiplied by an odd number. 3, 6. Still an even number. 2. Multiplied by another even number. 2. Maybe 4. So if you put x to be an even number, you always know you're going to get output another even number. Let's say, okay, fine, then I'll put an odd number in. Let's say x equals to 3. We're going to put an odd number. Well, you see this x minus 1? What's going to happen is that x minus 1, whenever you subtract an odd integer by 1, you're going to get an even number. 3 minus 1 is 2. You're going to see, oh, even if I put an odd integer for x over here from this x minus 1 part, you're going to get that even number. You're never going to get that odd integer. So B, no me gusta either. So A and B are out. Let's look at C. The product of 2 consecutive even integers. Well, you see what we did here? See what we did here? See what we did here? Look at this. Oh yeah. Oh yeah. I like that. What we did here is we disproved both C and D. Because product of 2 consecutive even integers, we're going to have x multiplied by x minus 1, right? If they're consecutive even or consecutive odd, you know that they have to have a difference of 2. Remember, we showed that before. Let's say, let's say 2. The next is 4. The next is 6. Or let's go the other way around. 1, 3, 5. There's always a difference of 2. What we have here is a difference of 1. So C and D are obviously knocked out. But we still have this. We still have E, the product of 2 consecutive integers. This shows us a consecutive integer, x, just needs a difference of 1. Let's say 1 times 2. We're going to get 2, and then we're going to get 2 minus 1. We see this difference of 1 here. So 10 is going to be E. So, yeah, that's all I have for today. And thank you for watching. Thank you for the support. Have a good day.